Okay, good afternoon. Let's continue. I want to pick up the pace a little bit, see if I can cover and, well, I won't be able to finish everything. I'm going to finish diode rectifiers and Zener diodes, at least two of the circuits. So let's get ready to rumble. All right. Let's see. Half wave rectifier with RC filter. There's a couple of equations that we're looking at. We spoke about the AC ripple. And then the AC ripple, of course, depends on the size of the capacitor that we are using. And then how long the diode conducts, right? So there are a couple of terms that are associated with this. Hopefully you're keeping up with your reading and you've come up across the terms called conduction angle and the conduction time. It's basically the time that the diode is going to be on and the signal is passing through. Okay, so you have conduction time, conduction angle, the ripple voltage, which is the size of the ripple from right there. That's the size of the ripple. It's also known as the peak to peak ripple. Okay, that's the sole AC component of that voltage. Okay, and there's an equation for that. Plus, there's also an equation for the size of the capacitor. All right, so let's just look at those quickly. First up, let's see. Conduction angle is defined as, or noted as, delta T. And then conduction, sorry, not conduction angle, conduction time, sorry, delta T. The angle is theta C. Ripple voltage VR is equal to Vp minus the diode turn on voltage, typically 0.6 or 0.7 volts for silicon, time period of the waveform divided by RC. That R is the value of the load resistor. Load resistor. So if you have already performed this in the lab, at least in my lab classes, we are ahead by a week. And so if you've taken my lab class, we already finished these diode rectifiers last week. So you may or may not remember, but we connected different values of resistors or load resistors on the output. When you connected different load resistors, you would see that the voltage discharges slowly. Anybody remember? 2.2 kilo ohms versus 150K? Yes, no, kind of. Everything's a blur at this point. Okay. Suffice to say, ripple voltage has an inverse relationship with the resistance and the capacitance, which again, explanations, the larger the size of the resistor or the capacitor, the slower it will discharge, and the slower that it discharges, the smaller the ripple voltage, right? So inversely proportional. That's the explanation. All right. Then we have equations for the current that flows through there. Ohm's law, V equals IR. So the DC current would simply be voltage across voltage divided by the resistance. The voltage in this case, of course, will take out some portion for the diode conduction. So it'd be Vp minus the on voltage for one diode divided by R. Again, that's straight from Ohm's law. In terms of voltage ripple, in terms of IDC, can be written as IDC times the time period over the capacitor C. And from there, we can define the capacitor as having a size of IDC times T over VR. So if you're a design engineer and you're trying to work, you have a goal, you want a specific amount of current to come out from your power supply, and then you only need a specific amount of ripple voltage, then that's how you're working. You're working backwards off of it, right? So you have IDC given to you, you have the time period, and then you have a specific amount of ripple that that needs to be within that range. Plug and solve. That's how you would work. For the most part, the ripple voltage actually does not matter, because to obtain a purely flat line, we would not simply just use a capacitor. We would actually take it and feed it into a Zener diode. So we'd have an absolutely flat line at the output. Okay. So the ripple voltage you could have a ripple voltage of 1 volt, just randomly saying. But if your Zener diode is within that range, then it's going to cut everything out, give you a flat line at the output. Okay. Separate question. How many of you have finished Zener diodes this week in the lab? And then the other students are doing it next week, right? You're not doing it next week either? Are you not taking 346? Yeah. You or whoever else who have not yet done it. Has everybody done Zener diodes this week? I thought some of the other labs were 1 week behind. How would that be possible? What? Who is? Did it do P-Spice afterwards? Okay. Simulations. That's not actually bad. That's a good experience, though. Maybe I should think about that. Anyway, let's come back. So so everybody's done Zener diodes then in the lab. Okay, so if you remember the Zener diode experiment, let's come back to the main point why I brought it up. If you remember the output of the Zener diode, right? Specifically line regulation. You applied a voltage and you varied that input voltage, meaning the line voltage that's coming into the circuit is going up, right? But even if it goes up, Zener diode conducts more current through itself and keeps the output voltage constant. So now let's think about if you have a ripple voltage, and even if it's a 1 volt ripple, large enough, right? And you have a 6 volt signal with a 1 volt ripple, and you only need 5 volts at the output. So you stick a 5 volt Zener at the output. No matter what the input signal is, it could go from 6 volts to 7 volts ripple voltage, but your output will be held constant at 5 volts. So what I'm saying is the size of the capacitor or the size of the ripple does not matter as much, right? You can attach a Zener diode at the output of a bridge rectifier, and we can obtain like a flat line. Okay, which is an experiment that is not in 346, but it's an experiment or a procedure that non-EE students do in their electronics class. They do a bridge rectifier, they do a Zener, and they join them together, and they get an output. So that's actually pretty cool. Yeah, that's a good question. Probably in semesters if you want to retake the class. No. All right, enough chit chat. Let's go back to here. So a couple more. Conduction angle is given by root of 2VR over the peak voltage. And then theta t, conduction time, in terms of the frequency omega. Hopefully you all remember all of this from 211 and 212. Omega is, anybody? Angular velocity, angular frequency, 2 pi f. And f is the frequency in hertz, but it's also 1 over the time period t. Everything is related. All right, and then finally, the peak inverse voltage or the peak reverse voltage that a diode must withstand must be a minimum of 2 times the peak voltage. Okay, 2 times the peak voltage. So a diode is non-conducting, but it also has it has the negative half cycle, so you get the VP, but now it also has the capacitor. The capacitor also has a peak value, and it's going to start discharging in the other direction. Okay. Most diodes, as I said, the standard silicon diodes start off at 50 volts. So that's plenty of leeway. Okay, let's see. Then the equations for center tap are still the same. VDC is VP minus V on. Still have one diode in each line. So in the center tap, my VDC can be given by VP minus V on. This changes, of course, for a full wave bridge when we have two diodes in each line. The ripple voltage is smaller. Well, not smaller, but the frequency is higher. It's twice. Times T 2C in delta T. The conduction time is 1 over omega 2 VR over VP. Okay, 2 VR over 2 VP. Now I'm writing the equations down here, but the equations are also there in the textbook. Right? These are standard equations. Okay. Right. All right. So now for the half wave rectifier and the center tap full wave, we only have one diode for each half cycle. So the voltage drop is only 1 V on. For a full wave bridge, there are two diodes for every half cycle. So it's 2 times V on. Okay, so there's 2 diode voltage drops. Okay, and so in a full wave rectifier, 2 diodes for each half cycle. So 2 diode voltage drops. Okay, for each half cycle. Actually, half cycle. Each half cycle. All right. And so the VP minus 2 V on, 2 drops. And IDC correspondingly, VP minus 2 V on for R. Ripple voltage, again, VP minus 2 V on over R, IDC, effectively IDC times T over 2C. And the other things remain the same. You got delta T, conduction time, is the conduction angle divided by omega, and this is root of 2 VR over VP. In the next slide, I have a summary of these equations, so you don't have to. I was going to say you have to memorize this for the exam, but it's an open book, so right here. Okay, simply lists a comparison of all 3 rectifier circuits. Modern power supplies, again, if you have an old charger lying around from like, one of your old mobile phones, just smash it open, break open the case, take a look at the circuit inside. At the front end, you should have a high voltage diode. It's a half wave rectifier that converts your 120 volt AC input into a half wave rectified DC output. It's rectified, and then the voltage is stepped down, and it's fed into a transformer. Okay, previous supplies, we used to have a transformer at the front end. We would step down the voltage first, and then we would perform the rectification. Okay, but the frequency is 60 hertz. The transformer size is large. When in modern supplies, when we first converted into DC, then we converted back into, I think I mentioned this, right? We converted into DC, then we converted into high frequency AC by using a transistor. And because of the high frequency, 600 hertz or higher frequency, the transformer size is smaller. And so that's the big difference between the older power supplies and the modern power supplies. Okay. Older power supplies that we used to get with our cordless phones and other devices, they would run on a specific voltage, meaning if you were using North American devices, you could only plug it into 120 volts. You could not take it outside without doing an electrical conversion. Now, the modern devices that you have, and I think I've stated this earlier, you can take a look at your laptop adapters and your cell phone chargers. It will say you can use it anywhere in the world. You can plug it into a 240 volt outlet and it'll still work. And the reason is the diode can handle, the first diode in the circuit can handle 120 as well as 240. So it simply converts it into half-wave rectifier, and then we convert it back into AC. And that's why we can use it anywhere in the world. Okay, so those are the uses for half-wave and full-wave rectifiers. Center tap is not used as much, again, for the reasons that I just mentioned, right? All right, Zener diodes. Everybody remember Zener diode operation, how and why they work? They are heavily doped. They are heavily doped PN junctions. They are specifically formulated to operate in the reverse bias. For those of you who are in my classes, if you did sweep and go, we performed the sweep and go operation from -7 volts to +1 volt. What did you observe about the forward bias? You didn't pay attention. Or, okay, let me ask everyone, what do you expect to happen in the forward bias? I heard short, I heard something else. What did I hear? Inductance? Conduct? Constant voltage, yes. The answer is it's made out of silicon. Regular silicon diode behaves like a normal diode in forward bias. So when we did the simulation from -7 to +1 volt, it's a 6 volt Zener diode. So it breaks down at 6 volts. So in the reverse bias, we obtain something like this. And forward bias, we obtain something like this. So regular diode around 0.6 or 0.7 volts. Okay. And so for Zener diodes, we can perform analyses in a variety of methods. One of the first ones is load line. Load line is something we did for the diode. And I mentioned at the time, we'll use load line analysis for Zener diodes. We can use it for FETs. We can use it for BJTs. So it's going to come up again and again, right? So in this case, we are trying to analyze the Zener diode using load line analysis, which is a graphical technique. The circuit conditions or the parameters provided are that we have a 20 volt source. Zener diode is rated for 5 volts. The resistance of the Zener diode is 100 ohms. And then, of course, it's operating in reverse bias. Okay. One important thing I want to point out at the top. Your V out is taken here. Okay, V out is taken here. Plus at the cathode and minus at the anode. Okay, because Zener diodes are operated in reverse bias. Okay? If you use it in forward bias, it's like a regular diode. But the Zener diodes are specifically formulated to operate in reverse bias. Right? Remember avalanche breakdown. If you're on Zoom, please send a test message in the chat. Thank you. What was I saying? Okay, yeah. So it works in reverse bias, but it's still a diode. So when we say that we are referring to the diode voltage VD of a Zener diode, the positive reference is still at the anode. Okay. So you see the positive reference is still at the anode. The only reason is because it's connected in reverse bias. And so VD and ID are shown as opposite of what the circuit is. Okay. In reality, what do we have? If you're talking about circuit current, the circuit current is flowing in this direction. But for the Zener diode, it's flowing in the opposite direction. Just some things to keep in mind. The reason is because reference for a diode always goes from anode to cathode. Okay, so V out is positive across the cathode of the Zener diode, just because it's used in reverse bias. It's plotted in the third quadrant. So we see the plot is here in the third quadrant. Okay, because it's minus V and minus I. Even though in the lab and in analysis, we'll measure and say that the cathode is positive. Okay, so I just wanted to point that out. So our Zener diode is rated for 5 volts. That means our V out must be 5 volts. RL or RZ is 100 ohms. That's the Zener resistance. That's the effective resistance of the Zener diode. That's the real life model. V out will equal VZ only when the Zener diode is on. The Zener diode is on only when V in is greater than VZ. Otherwise, the diode will be off, right? So V out is equal to 5 volts only if V in is greater than VZ. Okay. If it's less than VZ, then the diode is off and V out is simply equal to V in. Okay. So far, so good. Okay, so let's write the KVL expression and then generate our load line. Okay, so breakdown diodes operate in the reverse bias. Let's apply KVL around the loop. When you apply KVL around the loop, we obtain minus 20 and in order to avoid confusion, I'm going to follow what the book said. I mean, what the book explanation is. I typically apply KVL in a different manner. I mean, I take all the voltages on one side, then I just equate it to 0, and then I do my analysis. So my equation would be 20 minus VD minus VZ equal to 0. Okay, and I'm going to do what the book does so as to avoid confusion. So I would get minus 20 is equal to VD plus the resistor voltage VR. VR is nothing but 5,000 times ID or 5K times ID. So minus 20 is equal to VD plus ID times R is 5,000. That's my expression. Okay, that's my KVL expression. Again, as a reminder, load line analysis is a graphical technique that we use to solve for the values for diode voltage and diode current. There are two unknowns, VD and ID. If you are two unknowns, we need two equations. Graphical means we need two plots. One plot is this diode characteristic right here that is given to us. This load line, this must be generated. Okay, so in an exam or a quiz, you would be given the characteristic and would be asked to generate the load line. To generate the load line, you need 2 points. Those 2 points are the intersection points of the X and Y axes. To find those intersection points, we substitute the X value is equal to 0 and find ID. So ID would be minus 20 over 5,000. This gives me minus 4 milliamps. If X is equal to 0, what is the value of Y? And if Y is equal to 0, what is the value of X? That is effectively what we do for load line. And that's all we are doing. We find our equation and you plug in x is equal to 0, y is equal to 0, and find the value for the other coordinates. So now if ID is equal to 0, what is the value for VD? Simply equal to our supply voltage, or diode voltage. Okay. No, wait. Sorry. Yeah. If ID is equal to 0, then VD is equal to minus 20. Negative. But it doesn't interest. I mean, the graph that's given to us does not extend all the way to 20. So we need to find the point where it does intersect. And so we plug in a different value. Okay, we plug in a different value. We can plug in VD is equal to either -6 or -5. That's the limit of our graph, right? So we can plug in that value. So if VD is 0, ID is -4 milliamps. If VD is -6, we can calculate that. But if VD is -5, then ID is, plug in, -3, or and we get -3 milliamps. Okay. 20 minus 5, 15. 15 divided by 5 is 3. Okay. And so once we have those two endpoints, we plug it in there and we join those two coordinates and we obtain that load line. Okay. Once we obtain that load line, we look at the intersection point. And the intersection point, which is our Q point, what does Q stand for? Quiescent, yeah. Operating point, right? The quiescent point of the circuit, that's the operating point of the circuit. That operating point, like any point, has two coordinates, x and y. That gives us the value of the diode voltage and the diode current at that Q point. So it's labeled as IDQ and VDQ. Okay, IDQ and VDQ. So the intersection point of the load line and the characteristics. So the characteristics were already given to us. Those are the Zener diode characteristics, and that's the load line. Intersection point of those two gives us the VDQ and IDQ values. And in this case, I mean, of course, it's very hard to see or very hard to decipher, but this point, okay, this is -1, -2, -3, -4, and that's -5. And then this is slightly above 3. So this Q point is slightly above 3. So we could write it as 2.8, 2.9. It's not so far above that would be 2.8. So let's stick with 2.9. And this is the downside of a graphical analysis. Okay. If you don't have a zoomed in view of the graph or the chart, it's impossible to predict a accurate value. So in the intersection point, this is the Q point, and the coordinates of the Q point gives us the value of VDQ, or we could say VZQ, and then IDQ. IDQ is slightly above 3, so -2.9 milliamps. and VZQ is greater than 5, we could say 5.2, 5.3. I would say it's closer. Yeah, it's 5.2 or 5.3. Okay. It's a 5-volt Zener, but because of the constraints, meaning the applied voltage as well as the 5 kilo ohm resistor, the actual operating point of the diode comes out to be 5.3. And of course, the characteristics are a little bit exaggerated. So to have a slope in there, right? Real life Zener diodes may or may not have this kind of slope. Okay. So it may not have this kind of slope. Yes. We did. If VD is 0, we get ID as minus 4 milliamps. And you're saying, why do we set it at 0? To solve for the load line coordinates. So we have this equation from KVL. It has two unknowns. One is VD, the other one is ID. So we can plug in any value for VD and ID we want to solve for coordinates. Yeah. The reason we plugged in V, so the question being asked is why did we choose -5? Well, our graph only goes up to like -6, and so we plugged in VD as, we can plug in either at -6 or at -5, and then find the value for the current. So as our coordinate will fit and be visible to us on the chart. That's why we plugged in -5 volts. If you had more points to the left then we would use those points. Yes, answer is correct. Yes. What do you mean? We could use -4, we could use -3, we could use -2 also. Any one of them would work. Yeah, anyone. We just need to create a straight line. So load line is always a straight line. We can choose any point we want. Yeah. So we obtain the first point. Let me note it down. This is the first point, which is right here. When VD is 0, ID is -4, right? And then the second one is when ID is 0, VD is -20. Well, that would be somewhere to the left, right here somewhere. So it's not observable. It's somewhere to the left, right? I mean, we could take a chart paper and draw it out, but it's just easier to just plug it in within our range. And so then we plug in, if VD is 5 volts, then what is the answer? Well, it's like right here. This is 3. Actually, not that. This is 0.3. The goal is just to find 2 points on that line. That's it. There's 2 points on the line. Right? Question? Anyone? All right, we got 15 minutes left. So, piecewise linear analysis. Anyone hear of this technique before? Piecewise linear, kind of. Okay. The piecewise linear technique simply assumes, well, not assumes, but we have nonlinear devices, right? But, and this is again an important concept that we'll encounter later. If we look at a very small portion of the characteristic or a very small portion of the device over its operating range, we can treat it linear just for that portion. Okay. So let's take the case of a diode in forward bias, for example. If we look at a diode characteristic, overall that characteristic is nonlinear, right? But if we choose 2 points, let's say somewhere here and here, very close by, then we can treat this portion as linear. So it's a small piece of that device or device characteristic, and we can treat it as being linear within that portion. Okay. This is also the reason we can say that the diode has a linear static resistance, because it's linear between that portion. Okay. All right. So in this case, what do you see first? How have we modeled that Zener diode? So it's a constant voltage drop of 5 volts with a series resistance. The resistance, for all intents and purposes, we've kept it small. It's only 100 ohms. Okay. So still the same model as the previous problem. Exactly the same thing. The only difference is that we have a constant voltage drop. So it's a CVD model, constant voltage drop model, 5 volts voltage source, and 100 ohm series resistance. Okay. So we analyze the circuit, and before we begin our analysis, we make an assumption. Similar to the ideal diode in the constant voltage mode, is the diode on or is it off? If it's on, then it's conducting and there should be current flowing through it. If it's off, then it's off and there should not be any current flowing through it. Okay. And so, based on circuit conditions and the Zener diode value, what would be our logical assumption? On, right? There's only one answer, on. So let's assume that the diode is on. If the diode is on, then it drops a voltage of 5 volts. It has a resistance RZ of 100 ohms. So VZ is 5 volts, RC is 100 ohms. And that's it. We apply our circuit analysis techniques, Ohm's law, KVL, KCL. We apply it and we find the current through the circuit. If the current is greater than 0, it's positive, then our assumption is valid. If it's less than 0, then our assumption is incorrect. So we solve for IZ. Okay, we solve for IZ. So we assume that the diode is on. IZ or ID. Same thing, no difference. So we solve for that and we see, and we note whether it's greater than 0 or less than 0. Okay. All right. So apply KVL, simple circuit analysis techniques. If you apply KVL around the loop, I have voltages, I have minus 20 plus voltage drop across the 5 kilo ohm resistor. So plus IZ times 5,000 plus VZ is equal to 0. VZ, of course, is 5 volts. So it's 15. And I can say IZ is 20 minus 5 divided by 5,100. Oh, yeah. Plus IZ times 100. Forgot about the Zener resistance, equal to 0. And this is 15 divided by 5,100. So it's 2.94 milliamps. 2.94. And our conclusion is that Iz is greater than 0. Therefore, assumption is valid. Compare this with the previous graphical solution. What do you see? Or what do you note? Yep. So here the voltage we assume would be, not assume, we obtain from the graph is 5.2 or 5.3 volts. ID, the diode current, is 2.9. Here we have the Zener voltage of 5 volts. We simply take that. So VD is 5 volts. And then we calculate the current, which is 2.94. So two solutions of the same circuit, the exact same circuit. We have still got 5K and we had RZ of 100 ohms. And then here is the graphical versus analytical solution. Okay. All right. Questions? Anyone have questions? Any questions? I'm sure you have plenty of questions, but you need to let it sink in first. Yes. So let me see if I understand it. So V out is 5 volts and VZ is 5 volts, but then you said something about it being negative. Yeah, VD is just referring to the specific, because VD is I wouldn't say all purpose, but it's only talking about the diode itself. And so VD is always referenced with anode as positive. And for a Zener diode, we always use Zener diodes in reverse bias. And so VD technically in this case would be minus VZ. Yeah. So sometimes, yeah, it's tricky. So when I was a student, I was learning this for the first time. It took me just a hard time trying to get my head wrapped around everything. It's just a sign convention. That's all it is. Just because it's in reverse bias. That's all. Okay, 6 minutes left, so we probably don't have time to go to the entire solution of a regulator, but let me explain the operation of a regulator. Okay, Zener voltage regulator, right? This is one of the most important applications for a Zener diode. Okay, so as I stated earlier, we have rectifier circuits, and the output of a rectifier circuit is typically fed into a Zener diode, and the Zener diode is going to is going to conduct and is going to allow us to have a standard voltage at the output. Okay. Here's the thing, in terms of device physics, this is what happens, right? It conducts in the negative half cycle, right? So what is it doing? Junction breaks down. There's a huge influx of charge carriers crossing over the junction. Now, the reason why this happens is because it is a very heavily doped junction. So right from the beginning, it is designed to break down very quickly. Okay, very quickly in the sense, if we design it to break down at 5 volts, it's breaking down at 5, 6, 10, 15, 20, 200 volts, whatever the design could be, right? So the design includes both the physical dimensions of the diode, meaning the junction, as well as the doping or the dosage of the impurity atoms. Okay, that's the reason there is a presence of charge carriers, and it starts conducting at that voltage. So if you apply 5 volts in reverse bias to that junction, charge carriers are now tunneling through that junction and current starts flowing in the opposite direction. Now, once it breaks down and all of these carriers are crossing the junction, it's a huge amount of current that's flowing through. right? Charge carriers crossing the junction and flowing, that means it's resulting in current flow. So huge amounts of currents are flowing through, yet the voltage across it remains constant. And this property is used to maintain the output voltage constant in a circuit known as voltage regulator. The regulation part comes from the fact that you could have varying input, yet the input is regulated to give you a constant output voltage. Okay, so constant output voltage, so it's regulating the input voltage. And the way it does this is this. If we talk about having a constant output voltage, what does it mean in terms of the current? You have a specific value for RL. If V out is constant, what does it mean for IL? IL should also be constant. Okay, if V out is constant, then IL is also constant. V equals IR. R is not changing. If if VO is not changing, then IL is also not changing. But if V source, if the source goes from 5, 10, 15, 20, 25, 30 volts, and again, V equals IR, if the source voltage increases, what happens to source current? Source current also increases. Okay, so if Vs increases, then Is also increases. But if Is increases and you want to keep IL constant, where is that rest of the current going? Through the Zener diode. And that's where we use the property of the Zener diode in reverse bias. Because the Zener diode can maintain the voltage across itself constant while sinking a large amount of current through itself. So if Is increases and we apply KCL at the top, on the top node, what do we have? We have Is equals Iz plus IL. Is increases, IL is constant. That means Iz must increase. That's the only way that IL can remain constant. And if IL is constant, then VL, the output voltage, is also constant. Okay. So Zener diode operates in reverse bias. It breaks down. It allows a high amount of current to flow through itself, but maintains the output voltage. So when we did line regulation in the lab, you might have felt the Zener diode getting hot or warm. The reason was it's sinking more amount of current through itself. And because it's sinking more amount of current through itself, it's getting hot. And hence, all Zener diodes come with a power rating. PZ is VZ times IZ. It comes with a power rating, PZ, VZ, and RZ. So Zener voltage, Zener resistance, and the maximum power, PZ. That gives us the maximum current that can flow through that Zener diode. Okay, and we use that property to create voltage regulators, right? So we'll solve the rest of this problem on Monday. For now, we are at 4 o'clock, so we'll end class here today. We went by at a slightly higher speed today, just because the amount of material we have to cover. So review the lecture videos. I'll post it shortly after going back to my office in just a few minutes. Take a little break. Close your eyes, meditate, go outside, look at the sky, I guess, lay down on the grass if you can. And then after the break, hopefully you get refreshed a little bit, review the lecture video, review the textbook, and then prepare for the quiz on Monday, which will be based on the work that we've done here. Homework, I said that I'm going to push it back, so I'll make it due Sunday night. And so that way you have enough time to go through everything. If you have any questions, reach out to me. I should, yeah, I have my Sunday, I have few things going on, but Saturday I should be able to answer promptly. Okay. Sorry, what? Yeah, the rectifier. Yeah, the rectifier circuits. Yes. So have a good weekend, and I will see you all on Monday.